Can you please repeat that? And then-
All right, so if we took a spring and stretched it, as long as the velocity, as long as the speed's not zero, the thing's still moving. But we want that maximum. At the maximum speed, it will stop. Otherwise, it's not maximum. If the speed if we're still moving downwards, then we're not at the maximum yet. And now the argument is the same here, except use compression instead of stretching. Was that sufficient?
So the velocity, so the speed is the speed of this person?
Yes, speed of the person. I'm picturing he's running into the spring, and so the spring's compressing because he's pushing on it, and eventually it'll compress so much it will stop, and then be shot backwards.
Okay.
We'll talk about this being shot backwards in a moment. Other questions? So our formula has now been reduced to, he starts out with all this gravitational potential energy, and he ends up with all this elastic potential energy. Because we have conservative forces acting here, the energy is just being transferred from one form to another. So he starts out gravitational potential, that gets turned into kinetic energy at this point, and then it gets turned into elastic potential. But the total remains the same. We're left with mgh initial is equal to 1/2 k delta x final squared. And we're solving for delta xf, so delta xf equals the square root of 2mgh initial over the spring constant. So the square root of 2 times 70 times 9.8 times 15 divided by 40. That is a 2. Anyone else got the same thing? Okay. Units? Okay. So as he hit that spring, he is going to basically compress the spring half of a football field, and he will stop. Questions up to here before he gets slung backwards. Just before he hits the spring, how fast is he going?
31.6 per second.
All right, so now he gets slung backwards. He's basically pushed. How far up the hill will he go? So he compresses the spring then basically pushes back, and so he's slung backwards.
Will it be all the way back to the top?
The question was, how far up the hill will he go? Back to there. Now, somewhere along the journey, we're ignoring air resistance, but somewhere along the journey, a gnat lands on his back or front. He lands on him from this direction, basically gives just a tiny bit of force in that direction.
What?
A gnat. Just a tiny little bug. So we now have a non-conservative force introduced into the system. When the gnat lands on his back and pushes him in the direction he's going, does he gain energy or lose energy?
He loses the energy going in that direction
Why?
because the net is pushing against him.
Push it. I want the gnat pushing him in the direction he is going. Were you picturing that he was going back like this and it lands on his back?
Yeah.
Oh, yeah, my wording was off there to start with. Okay, it lands on his chest as he's going backwards.
But that bug has a very little mass, no?
It does have very little mass, but the bug is pushing on him. So he's not gonna gain much energy, just a tiny bit. Because he's being pushed the direction he's going. Which means if he starts at the very peak here, he's gonna have just enough energy to go falling over. And how fast is he going when he lands down here?
31.3.
Fun with energy. Questions to hear? All right. I know you're pumped. You got real excited here. We got some energy going. And it's time to take a break.
Yeah, but together. No space, yeah.
Question for you?
Yes.
So the lecture just before this one, is that this series of videos?
I like this.
This series of videos right here?
So the, I think so.
Cause I'm just trying to, cause I'm
calculus.
struggling right now.
So the last week, would have been six. Yeah, so that should be.
So
For
that's
example,
10 series.
yeah.
The KI view.
The why?
Categorize everything on here.
I'm
confused with
They're
that.
parallel.
sorry,
Theory,
if I need to do
that if
some
it's parallel,
heads,
then
I-
it equals zero. But they
there
don't want
was
to say
one
that
where
on the bracket.
there was a quiz.
I should have said.
Yeah, I guess.
Damn, I was really.
Yeah, so I.
Yeah, yeah.
That's crazy.
All
Like,
positive, yeah.
yeah, it's just
Everything.
crazy.
Didn't really look at it from the top of my head.
Can't wait for
Linear algebra.
Okay,
So it's gonna be
That'd be horrible.
If you go to the Blackboard page under lectures, then there's the select footage from fall 2020 lectures, and then all of them will be right there together.
Gotcha. Okay, cool, thanks.
All right, I'm gonna pause this. Would someone please remind me? All right, so just a typical problem. So in terms of forces acting on it, what are the three forces involved in this problem?
normal, weight, friction in the second one.
Yeah, the second one. So normal, weight, friction in the second one. One more force involved.
Would there be tension on the spring or?
At that point, sort of an ideal elastic. You've missed 30 seconds. Two of them are conservative. One of them is non-conservative, the normal force, but the normal force doesn't do any work. It's a lazy bum. So, energy is conserved. So for part A, E initial equals E final. Surprise, surprise. A initial plus U initial equals K final plus U final. Same startup as we had before. Matter of fact, since there's a spring and a change in elevation involved, it looks exactly like we did before. And I know you're really pumped to shout out 1/2 mv squared. I assume you did it in your head in unison. mgh initial plus 1/2 k delta x initial squared is equal to, well, that except final, 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. And our traditional, what can we get rid of? initial that.
And final velocity?
Same reason as last time. If VF is not 0, that means the spring is moving, which it's going down the ramp, it's still gonna compress more. If it's coming up the ramp, that means it was compressed more.
The initial spring, I don't know how you would say it,
The initial elastic potential energy.
The final height.
You wanna make final height 0?
Yeah.
Okay.
Question, that, 40 meters, is that the length down the ramp or the length? or
That-
the height
that
of
is-
the-
That is from the leading edge of the box till it hits the spring.
Oh, okay, alright,
So from there to there.
gotcha.
Now, making the final height equal to 0 is not necessarily I do not find it as intuitive as a different spot, but there's absolutely nothing wrong with this. So it all depends upon where we're gonna stick an extra variable. All right, so this is what we're left with here. So recognize that it's going to compress a certain distance. We don't know what that distance is. Now, I labeled it as delta x sub f over there. I'm just gonna label it as x, just to save on writing. I'm not worried about the size of the box or the size of the spring. We're not gonna get into that level of subtlety. So that's basically where it's coming to rest. All right, so if h is equal to 0 here, what is the initial height?
X plus 40.
No. Why is it not x plus 40?
Just
that
because
it?
that's the distance up the ramp and not the height of the output
Yeah,
from the ground.
we need this distance. So we basically have a triangle here. The hypotenuse is 40 plus x. This angle here is 53 degrees. And we want to know that. Well, I know it's less than 40 plus x. So this becomes 40 plus x times the cosine of the angle.
Sine? Nothing.
Oh, yes. Stand your ground. Sine. Times the sine of the angle. And that's gonna be equal to 1/2 k delta x final squared. Or actually, since how I have it labeled there, k x squared. I personally would have chosen h is equal to 0 at this point right here. And the initial height would be 40 times the sine of 53 degrees. And the final height would be x times the sine of 53 degrees. It really does not make a difference. You still end up in the same place. But that to me just is the way my mind latched onto it. So, well, depends on what point you want to start sticking all the numbers in. Why not now? So I have 5 times 10 times 40 plus x times the sine of 53 degrees, which is about 0.8. It's equal to 1/2 times 30 times x squared. So 1600 plus 40x is equal to 15x squared. X squared minus 40x minus 1600. 5 times 10 times 0.8 is 40. Distribute that. Okay. We will have two answers, one of which will make sense to the problem, one of which will not. No, that's not right. B squared is 1600 minus 4AC. Yep, there we go. So when somebody has the square root part, they share.
Um, 312.41.
So we have 352.41 over 30, or negative 272.41 over 30.
11.75. Hold on.
What you got?
I got negative 9.08.
Oh. Yeah, 9, not 10. All right, units are, yep. Which is the correct answer?
Negative 9.08,
Why?
because it goes down.
And where do we make down negative?
Just now. Just now.
Whichever answer we like, we'll just rationalize it, but.
Is it because the spring gets smaller, so then it's minus?
Think about how we defined X.
The positive.
It will be under it, the initial stop will be under it, wouldn't
So the initial, say it again, Courtney?
it? After stopping, like the spring as, when it's fully compressed, won't that be under zero?
Why? Why?
Wait, that wouldn't be true if we set H equal to 0 at the place where the spring stops before rebounding, right?
Why would it be negative?
Why would it be positive? Just as a hint, it is one of those, assuming that there was no Carroll's math error, it is one of those answers. It is either the positive or the negative solution. It's not some trick question where it's both, or neither. And then the CIE comes in, kills everybody.
You selected H equals 0 on the bottom, no?
Right.
Then going up is positive.
So if we're saying that X is negative, we're saying that the distance there is negative, which wouldn't make any sense, so it would be the positive number, right?
So if,
The change in
If-
distance from at rest to, once it's compressed, if you say that's negative, that's a stretch, wouldn't it be?
it would be, where does that show up in the math? At what point in the math do we make the positive solution the
Then we
correct
have
one?
the 40 plus X
Yes.
sine theta.
That's how much it compresses. 40 plus some amount. If it is the negative solution, that means that it's compressing 40 plus negative 9, or 31 meters. In other words, it's,
Well, it's not that it's compressing that, but it's
Oh,
traveling
yeah.
that distance.
yeah,
right?
so that's where it is when it stops compressing the spring. It is the positive solution, because of how we defined X. It's not a matter of what we decide is the positive or negative direction. Again, we're dealing with scalars here. The only thing that is built into it is that when we're dealing with gravitational potential energy, when we get farther from the planet, H better be a bigger number. Even if we chose H to be 0 here, then H down here would be a negative number. But that's the only thing that's sort of set by the nature of the definitions.
So if we instead said H equals 0 at, where you were saying that you would have, would we then have taken a negative solution, or would it just?
It'd still be the positive solution. The difference is that it would be mg times 40 sine theta is the initial potential energy, is equal to mg negative x sine theta plus, it'd still be 15x squared. And the nature of the fact that I may put a negative here means I want the positive solution.
Okay.
Alright, so that is the correct solution. But what is this? What is the physical meaning of this? So 11.75 meters is, 11.75 meters is how much it compresses, but this negative answer with the spring out here, what's happening there?
Is that how far out it would stretch before returning to, center once the, mass comes up off of it?
I had a slightly different thought in mind. Let's see. So if it's not the point at which the mass would come off of it, it's if the mass stuck to it, it's how far
And
up the
then
mass would
stretch
go.
Okay.
If the mass did not stick to it, then the mass would come off at this point right here.
Oh, okay.
Because because the spring is basically, it's speeding up to that point. At that point, that it reaches equilibrium, then the spring's gonna start to slow down as it stretches, and the box will move at it, whatever it's doing.
So if you set the spring up on the other side and attached it to the mass, would it stretch by that much?
If I put the spring, started out attached to the spring,
Yeah.
it wouldn't be the same because it doesn't have that going for it.
Okay.
It's built up some steam by the time it hits the spring here.
Okay.
All right, questions about this before we throw friction into it?
If, the mass didn't like have enough speed to get back up off the spring, would the second answer be right? Like if it wasn't attached, but it fell onto it and then.
All right, so how would that show up? No, it'd have to, because we're not losing any energy here. So whatever energy it had just before touching it, it has a certain amount of speed, and the spring is not, well, actually, the spring's not moving at that point. It should just reverse its process. The process should just reverse. Now with friction, we'll come up with some indication potentially if it's not enough to, it would not get slung back. But without friction, it should, the process should just reverse itself. Did I answer your question?
Yeah.
Okay. And I did start this, didn't I? Yeah. Other questions before we throw friction into it? All right, we will be writing a lot of the same stuff again, but we'll start with cleanish slate. There is obviously a difference between the two problems. All right, so now friction is involved. Friction is definitely a non-conservative force. I know that non-conservative work is equal to E final minus E initial. In other words, whatever my initial energy is plus the non-conservative work is going to be equal to my final energy. So we do have this extra term in here. As the box comes down the ramp, which way is friction acting on it? Okay. Since displacement is down the ramp and friction is up the ramp, what do we know about the work done by friction?
Gonna reduce displacement, is that what
Oh, reduce the final answer?
you? Yeah.
Yes, I was hoping for something intermediate, but yes, that is true. What does it tell you about the sign of the work?
Negative.
Yeah, that's what I was shooting for. Because it's negative, we end up with less energy, so it will not go down as far. The friction, there's no reason for the friction to change. We're assuming that we're not sanding off the bottom of this thing, so we're changing the surfaces. We're assuming friction's constant. So we got this initial kinetic plus this initial potential plus the force done by friction. Write that slightly differently. Friction times the displacement. Ooh, I have two different x's here, so. Oh, instead of using x, let's just use r. Oh, no, s, like that one better. F dot s is equal to k final plus u final. And let's just say, the last time tonight, there will be other times, but the last time tonight, here we go, you're gonna dazzle me. What's the formula for kinetic energy?
1/2 mv squared.
I'm close to dazzle then, appreciate it. So 1/2 mv initial squared plus mgh initial plus 1/2 k. Little k, delta x initial squared plus, well, actually, at this point, let's go ahead and do the substitution here. Friction is up the ramp, displacement is down the ramp, opposite directions. The cosine of 180 degrees is -1, so negative f delta s equals 1/2 mv final squared plus mgh final plus k delta x final squared. What can we get rid of?
Initial velocity.
Apparently writing with white. Oh, I don't want maintenance to have to deal with that. I feel like there's a time in my life when I would have hit that every time, but I suspect that's just selective memory. All right. All right, so initial speed is 0. We got rid of that. What else?
Delta x, the initial.
Okay.
Final height is 0.
Get rid of one more thing.
Is it final velocity?
Speed. Yeah.
Final speed.
So we are left with mg. Initial height, we've already gone through that. The initial height is 40 plus x times the sine of theta, 53 degrees. I guess officially I didn't define it. The math guys will not be pleased about that. All right. Minus the friction. What is friction? Well, that's just UK times y, delta S. Is equal to 1/2 kx squared. And we're solving for x, so what's the normal force? I got this y in the formula here. What does it equal?
mg sinus theta.
You said
Is
mg,
it-
which
is the weight, no?
it is related to the weight, but it's not
Yeah.
equal to the weight.
Yeah, I know, let me just draw it. And this yeah, it goes also, it just goes also with the sinus, I think.
Also with the,
Mg sinus theta also?
no, not sine.
No,
Yeah.
cosinus?
It is cosine. Sine of theta, if we break the weight up, weight is acting down. If we break it up, we have m, that's mg there. Mg sine theta is down the ramp. Assuming that we're given the angle with respect to the horizontal, this is mg cosine theta.
Okay.
Minus UK mg cosine theta times, what is delta S?
Well, if friction